Hi everyone, my name is Wiagil Widoyoko, student ID 131182004, and I will be presenting on my practicum assignment regarding the effects of pipe length, valve type, and its opening on the overall head loss in a pipe system with incompressible flow. This experiment aims to provide the following learning outcomes. One of the objectives is for practitioners to complete this experiment with a better comprehension of incompressible fluid flow and its properties in a pipe system. Secondly, is to determine the friction factor and equivalent roughness of PVC Class AW pipes. Then, to find the overall head loss of fluid flow in pipe systems where the pipe length and flow are varied, as well as to analyze and compare the results. Lastly, is to determine the loss coefficient of valves present in the pipe system. Before starting the experiment, allow me to brief you on some basic theories. In solving problems related to pipe systems, a form of the Bernoulli equation, known as the mechanical energy equation, is generally used. More precisely, the head-based, no-shaft-head form of the mechanical energy equation presented here. Since we will be dealing with horizontal pipe systems with constant diameter, we can cancel out the heights and the velocities to have a more simplified equation. The HL denoted here represents the overall head loss. They exist due to the presence of viscous effects, i.e., frictional resistance in piping systems. The overall head loss is the sum of all the major loss and all the minor loss of the pipe system. Major loss is present in all pipe systems as it is a loss due to frictional resistance between the fluid flow and the walls of the pipe. Its value is influenced by the roughness of the pipe material. Using this Darcy-Weisbach equation, we are able to find the friction factor. Then, we can calculate the equivalent roughness of the pipes by using the Colebrook formula under the condition that the fluid flow in the pipe is turbulent. We can check whether the flow is turbulent by finding the Reynolds number beforehand. If the value is greater than 4,000, then it is safe. The figure on the right is known as the Moody chart, which shows the correlation of the friction factor to the Reynolds number and relative roughness of round pipes. The non-laminar range of the Moody chart is actually a graphical representation of the Colebrook formula. Now to minor losses. Minor losses occur due to the presence of pipe components and fittings such as elbows, tees, and valves. The formula to find minor loss is shown here, where we can see that it's functionally related to a variable known as its loss coefficient, which is denoted by KL. The general values of loss coefficients for common pipe components are shown here. In the case of valves, the loss coefficient is also dependent on the valve opening. These pictures below depict a gate valve when it is at the fully open position and at approximately the half-closed position.
Okay, so in this segment, I will walk you through the apparatus and measuring devices we will be using for this experiment. The first one is the hand blower. So the hand blower will act as the source of incompressible flow, and in our case, airflow, throughout the pipe system. And then we have a reducer socket. So the function of the reducer socket is to mitigate any leakage of air between the outlet of the hand blower and to the pipe that it is joined to. And then we have our first measuring device, which is the digital anemometer. The function of the anemometer is to measure flow velocity of different points throughout the pipe system. So in our case, we will be measuring the flow velocity at the outlet of the blower, as well as the flow velocity at the output of the pipe. And then we have the most important measuring device, which is the manometer. So the manometer functions to measure the pressure drop between 2 points in the pipe system. And it will be connected to the pipe system through this hose. This hose will be connected to our version of a pitot tube. So because we found difficulty in finding the pitot tube that you would generally see in textbooks, we have opted to an alternative solution, which is by using a copper pipe and a copper elbow. When we assemble these together, they resemble a pitot tube and actually serve the same functions as a pitot tube. And then we have our valves. So in this experiment, we will be using two valves. We will be using a ball valve as well as a gate valve. As you can see here, this is the gate valve, and these are valve sockets. So we are able to connect the pipes of the pipe system to this gate valve. And yes, that's about it.
In this video, I forgot to mention the pipes. The pipes we will be using are 3/4 inch in diameter PVC Class AW pipes. Here is a schematic of the experimental setup, and these are the tests that were conducted in this experiment. As you can see, there is a variation in length, variation in valves, as well as variation in valve openings. The first test was conducted to find the friction factor and the equivalent roughness of the pipe. The manometer reads the head loss of the testings in kPa, so all head loss readings are converted into meter. With knowledge of the flow velocity and head loss, we are able to find the Reynolds number using this equation and the friction factor using this equation. Then keying in F and Reynolds number to the Colebrook formula to find epsilon. The obtained average values of F and epsilon will be used for the preceding tests. The second test was performed with a fully open ball valve. With knowledge of the friction factor, we are able to find the major loss of each interval using the Darcy-Weisbach equation. Then we can subtract the major loss from the overall head loss to obtain the minor loss. Using this equation, we can then calculate the loss coefficient for each interval. The third test was conducted with a fully open gate valve. The data processing of this test is identical to the previous section. We will use a gate valve that is half closed for the fourth test. This requires velocity readings at the blower outlet as well as the pipe outlet of the experiment. Then, using the mean value of flow velocity for data processing. The steps for data processing are practically the same to the previous testing. Now, tests 5, 6, and 7 are basically the same as tests 2, 3, and 4, but the total length of the pipe system used is 1.6 meters instead of 2 meters. We can also see here that the gate valve is being positioned to be half closed before starting the experiment. From the data processing, we can conclude the following. The experimental value of equivalent roughness is almost 10 times the theoretical value. This increase could be due to the presence of impurities within the walls of the pipe. Location of the experiment could also play a factor, as these experiments were conducted outdoors, where it is more prone to collect dust. Now observe the similar tests of varying lengths. It can be seen that the overall head loss experienced by the longer pipe is greater than that of the shorter pipe. This proved the mathematical statement of the Darcy-Weisbach equation as well as the function of pressure drop, which shows that head loss is directly proportional to length. It can also be seen that the overall head loss experienced by pipe systems with valves is greater than that of the pipe system with no valves. The presence of valves and the assembly of the pipe installation causes this increase in head loss, as air could possibly leak through any loose holes or connections. The results of loss coefficients obtained are much greater than the typical values. The results of loss coefficients obtained are much greater than the typical values. This may be the result of inaccurate opening of the valve gate, as there is no way of making sure whether the valve is accurately positioned at half closed. As a matter of fact, the obtained value of loss coefficient for the half-closed tests are much closer to the theoretical value of the 3/4 closed valves. These are the conclusions that answers the objectives of the experiment, which I will not go too in-depth as they have already been explained in the previous section. In terms of how to improve this experiment, I would suggest to clean the inside of the pipes to rid of any impurities that could disrupt the value for equivalent roughness, and to use seal tape, which acts as a sealant in between valve and pipe connections, or any kind of sealant to reduce air leaks. And that wraps up the presentation. Hope you learned something new. Thank you for watching.